Hi everyone, thanks for checking out this video. So in this lesson, we're going to implement matrix addition for our tensor data type we're working on. So I told you guys before that when we're doing values, we started with addition because that was like the easiest. But for tensors, in the last video, we actually started with multiplication because I said for addition, there's a little bit of an extra complication. So before we actually start writing the code, I'm going to show you guys this complication that I'm talking about. Oh, and just before we even get started, yeah, just make sure you guys have all the previous code. Just make sure you run that at the top so we can keep using it. Okay, so the complication that I'm talking about is what's going to be called broadcasting. Okay, but before we even get to that, I'll just show you guys what like the most basic matrix addition looks like. So for now, we'll just define a couple Julia arrays, not even using tensors yet. Just a couple arrays. I'll just call it like A equals 1.0, 2.0, 3.0, semicolon to end that row, and then 4.0, 5.0, 6.0. Okay, and then make another one called B. And just to make a simple example, I'll just make it all, I'll make the first row all ones and the second row all twos, so we can kind of see what's supposed to be happening. Okay, so print A, and then, okay, okay, and then we'll say C equals A plus B, and then we can print out C, so this should be the sum of the two matrices, and yeah, so when we add two matrices together and they're the same shape, it's just an element-wise addition, so it's just the first element plus the first element, second element plus the second element, third element plus the third element, and then yeah, it's just element wise. Every element is being added to the corresponding element in the other matrix if they're the same size. So when we have two matrices that are the same size, this is very easy for us, right? Because it's just element wise addition, very, very easy. But the thing is, we want to have a little bit of extra functionality so that we can do what's called broadcasting. So this is our simple case. I'll just maybe notate it up here. So I'll say like simple case A and B are same shape. And then broadcasting will be our next example. So what I mean by broadcasting is, okay, let's say that A is the same as before. It has two rows. This is the first row and this is the second row, and then three columns. So that's 1, 2, 3. Every row has three columns. But let's say B has three columns but only one row. So rather than having the same shape as A, B has a column for every column in A, but only one row. So when we see something like this, we want to be able to still do the addition, but do it in a way that automatically broadcasts B, so that we're adding B to the first row of A and then B to the second row of A. So we just it's called broadcasting. Just broadcast B to the first row of A and then to the second row of A. Okay, so I think Julia does this automatically. Let's actually just see if this works. Whoops. Oh, sorry guys. I think we need the period here actually to make it to get the broadcasting to happen. Yeah, so when we have this period plus, it actually does the broadcasting automatically, and we could have had the period up here too, I think, without changing anything. So we could have had this also be could have had that also be the period and still get the same correct answer for the simple case too. But yeah, when we have this A plus B where B needs to be broadcasted, Julia will do that automatically for us with this dot plus. So we want our tensors to be able to do that too. This will just make it a lot easier because when we're doing when we're eventually doing the neural network example, we're going to do what's called batching of samples. So we're going to have like a matrix where every row is going to be representing one sample within the batch going through the neural network, and we want to be able to like add the biases for each neuron like to all of the batches by like broadcasting. So this is going to be something like some functionality we're going to need when we actually do our neural network example, and this is something that like machine learning libraries like PyTorch also like automatically do for you. They do this like nice like shape broadcasting. So we want to make sure our tensors can also do this. So that's the complication. It's not going to affect our forward pass too much, because when we do the forward pass too much, it's just going to, when we do the forward pass, it's just going to look like this, where it's going to be like dot plus, and then Julia will just do the broadcasting for us automatically. But it is going to make the backward pass more complicated, because when we do the back prop, we're going to need to like do like reverse broadcasting basically. So that'll be the complication for this video. Again, it's like I keep saying to you guys, now that we're dealing with tensors rather than values, the difficult part is not the concepts, because we already covered with our values like the concepts of operation tracking and forward and backward passes. So we did all that already, but now the only new difficult part is just the complicated arithmetic of dealing with arrays, basically two-dimensional arrays, and this video is going to be an example of that basically. Okay. So let's get into it. So first thing to do, we'll do our forward pass again, just like we've been doing. We're going to copy and paste our value code and just make a couple easy small changes. So it's going to copy and paste this addition code for values. I'm going to copy that down here. And then, yeah, just a couple small changes to make. A and B are both of type tensor. Yeah, we're doing the same thing here, getting the output array first. Remember, we need the dot plus so that it'll do the broadcasting for us automatically. Maybe I'll like leave a comment like that too. Broadcasting happens automatically in case of row vector. Okay. And then result's going to be a tensor this time. Out is going to be used as the data, like result.data. It's also tensored, even just for the comment, I'll change it. For grad, we can actually copy and paste our grad code from here. We're making a grad just to be like a placeholder of zeros. But we want this zeros array that we're using as the placeholder for grad to be of type float64 and have the same size, meaning the same shape as the output array that we just calculated. And the operation is plus with operands A and B. And I'm going to remove this comment because it's not a value anymore, it's a tensor. And yeah, I think that should be good for the forward pass. And then okay, now it's time to do the backward pass. So to do this part, yeah, again, just gonna copy and paste some code we've already written basically from our values. So grab this code up here, the backward pass for the values. Okay. I'll say just adjusting the comment here. So this backprop is called on a tensor, where we have a tensor which is A plus B, where A and B are both also tensors. And then we call backprop tensor, and then it updates A.grad and B.grad. And remember, everything here is a two-dimensional array. So tensor A and B and A.grad and B.grad are all two-dimensional arrays that we're dealing with here. Okay, so a couple of small changes to make first. So first of all, it's going to call this tensor, and it's going to be of type tensor with some operation type. Again, this multiple dispatch function of Julia, we can have the same function name defined to do different things for different types of inputs we give it. So we're taking advantage of that. So we're defining backprop to do something now when it sees an input tensor that is, of course, of type tensor rather than value, and where it's a tensor that was created from an addition operation of other tensors, basically. Okay, here's the complicated part, and I apologize to you guys, but I'm going to copy and paste this part, because yeah, it is a bit complicated, and unfortunately, it's again similar to last video. This might be something where it's not very intuitive, so I'm going to ask you guys to either take my word for it, or do a little bit of work on your own to kind of prove this to yourself. But the tensors we're dealing with now are a little bit too complicated to be doing like writing our own tests to prove it to ourselves for every video we do now. So I'm just going to ask you guys either to take my word that this code is correct, or to just kind of work through it yourself and prove to yourself why every part of this is happening. But yeah, basically for each one of the operands, we need to update a.grad and b.grad. But we can't actually just say A and B because there's no A and B here. What we have is some tensor input, and the way we get to the operands that were used to make this tensor are by going tensor.op.args, and that gives us a tuple that looks like A comma B tuple. So if we take the first element, that'll give us A basically, or I'm just calling A like the first operand that was used to make tensor. And then A.grad will allow us to update the gradient of A, or the gradient of the first operand that was used to make this tensor we're dealing with. But for each one of these, so first we're doing A, like this all here is updating A.grad basically. And then this all here is updating B.grad. But for each one, we need to check basically to see if we need to do this reverse broadcast or not. So basically we're checking to see if the size of the tensor.grad, the input, if this is the same size as the size of the operand A. So basically, and you could have written, because tensor.data and tensor.grad are the same size, you could have written tensor.data here too, and that would have also been okay, but I just wrote tensor.grad. We're basically checking to see if this is the same size as the operand array, basically. I think we could have written this even more simple. I might actually change this code later on to even make it more simple. But yeah, I'm using the code right now that's like up on my GitHub for this actual package that I made. I think we could have made this even more simple though now that I'm looking at it. And maybe I will make this improvement in like a future version, but I think we could have even just said size of tensor, because we can do this now. We added this functionality, equals size of tensor.ops.args first element. I think we could have written it like that. That would have been even simpler. So I wrote it a little bit more complicated than it needs to be. So I might make that change later on, but for now, I'll just leave it like this. But yeah, basically this is saying like, okay, if they're the same size, then we update the gradients this way, which again, not very intuitive, but you guys might need to either just take my word for it for now, or just prove it to yourself. That's why we did the values for so many videos. The values were easy to understand what was happening intuitively. This is not so easy to understand intuitively, so yeah, you guys might need to take my word for it, or prove it to yourself that this is how we update the gradients. But yeah, if they're not the same size, then we need to do this reverse broadcasting basically. And yeah, this is the code. Again, not very intuitive, but basically we need to like condense, like do like a summing up to condense the dimensions of tensor.grad before we multiply tensor.grad by everything. Again, not very intuitive. Hopefully you guys either take my word for it or just prove it to yourself while we're doing this. But yeah, this if statement is checking to see if we need to do that reverse broadcasting to account for like a broadcasting situation or not. Because remember, what I mean by broadcast is to do the addition where A and B are not the same size as each other. And then, okay, this if statement here is just doing the same thing, except it's updating b.grad. So for b.grad, we again do the same thing, check to see if the shape of b is the same as the shape of this tensor. And if it is, we do a regular gradient update for b. And if it's not, then that means that we broadcasted in the operation, and we need to do this like reverse broadcasting situation that involves summing up tensor.grad before multiplying, basically. Okay, so I realized that was probably super confusing, and yeah, I again apologize to you guys for this part being confusing. It's not very intuitive. It's also hard for me to understand everything's happening intuitively. Maybe it makes sense to you if you're like very good with like matrix operations and like visualizing them and stuff. But for me, I find it confusing. I find it difficult to like visualize in my head everything that's going on. But yeah, this was the point of why we did all those videos with the values, was because the values was doing all these things with single numbers first, so that we could understand what was happening. And now that we've proven all these concepts to ourselves with the values, now we're like extrapolating them to the arithmetic of two-dimensional arrays, basically. So yeah, it's probably not intuitive, but hopefully you guys are kind of understanding at least the process of like the forward and backward passes and operation tracking, just because of all the stuff we did with the values previously. Okay, so I think that's going to be it for this video. Again, sorry we're not like testing all these individually. With the tensor data type, we're going to just write all of the operations, and then at the end we're going to do a final test where we actually write a neural network and actually solve like a deep learning problem with neural networks that we write with these tensors we're making. So that will be like the final test, but we're not going to individually test all these, just because, like I said, they're not as easy to test as the values, basically. Okay, just as a reminder for you guys, all this code's up on my GitHub. The link will be in the description. And just as a reminder too, all this is based on my SimpleGrad package that I made. So here's the GitHub here. Yeah, it's a real package in Julia. You guys can like install and use if you want to. It's meant to be usable for real applications while also being very easy to understand and like educational. And I also have yeah, the documentation site over here. Yeah. So thanks for watching, guys, and see you next time.